Okay, first equation. Acceleration. Junior cert definition for acceleration is change in velocity. Change in velocity divided by time. Change in velocity divided by time taken. Using a uvast then, acceleration equals change in velocity is the final velocity minus the initial velocity divided by time taken is t. Okay, bring across the t, it'll become a t equals v minus u. Then bring across that u, it'll become u plus a t equals v. Or just rearrange it, v is equal to u plus a t. That's our first equation there. Okay, second equation. We're going to use average velocity. Average velocity. Now, if you're accelerating, your velocity is increasing. How would you get your average velocity? Well, you simply add your starting velocity and your final velocity and divide by 2. That'll give you your average velocity. So it's equal to your starting velocity, which is u, plus your final velocity, which is v, all divided by 2. And that'll give you your average velocity. Okay. Now, junior cert formula for speed was speed is distance over time, and velocity is displacement over time. Okay. So another way of writing average velocity is equal to displacement over time, which is s over t. Okay, s is our displacement. Okay, so we have two equations here now that both have average velocity in them. Okay, so I could make the two of these equal to each other. Okay, s over t is equal to u plus v over 2. Okay, now for this equation I wanted it all in terms of s, so I'm going to leave the s here and bring the t across, so s is equal to u plus v over 2, all multiplied by, when the t comes across, it's going to be multiplied by t, like that. Okay, now I've already, back up here, our first equation we derived was this equation for v. So I'm now going to take this equation, I'm going to stick it in instead of this v here. Okay, I'm going to substitute it in there because I want to get rid of that v. Okay, so instead of this v, I'm going to write u plus at. So let's just see what we have now. So s then is equal to u plus this, u plus at, all over 2, and it's still multiplied by the t. Okay, I'll just tidy this up. So u plus u will give you 2u, s equals 2u plus at all over 2, all times t. Okay, and I can write this, so multiply all this by t, so that's going to become, so 2u times t will be 2ut, still over 2 now, plus at times t would be at squared. Okay, so s is equal to 2ut plus at squared over 2. Okay, now write this to two different fractions. S equals 2ut over 2 plus at squared over 2. Okay, the 2's there will cancel, and that gives me s is equal to u times t plus, now dividing by 2 is a half, so it's like multiplying by half, so it's a half of at squared. S is equal to ut plus a half at squared. Okay, and that's our second equation. Okay, and the last equation, we start with the very first equation that we derived, which is this one here. So v equals u plus at. We simply square both sides, so that becomes v squared equals all of this here to be squared. Okay, now if you have two things in brackets that you square the first, so that becomes square the first times u squared plus 2 times the first by the second, which is plus 2 times the first times the second, plus the second one squared. Now if you square this, you get a squared t squared. Okay, at times at will give you a squared times t squared. Okay, now nearly there. Look at these second two terms now. We've got a in both of them. We're going to take out 2a out of these last two terms. Okay, v squared equals u squared. Leave that as it is. Plus we're going to take out 2a. Okay, now it doesn't look like there's a 2 in here. Okay, so we're going to have to do something a little bit clever to take out 2a from here. So right here it's easy. So take the 2a out of here. You're left with ut. Okay, 2a times ut will give you 2uat. Now what do I do here? Well, if you take out the a, it'll leave you with a. You're still going to have your t squared. Now, what do I multiply this by to get a squared to t squared? Well, a times a will give you a squared, t squared. I'll have to get rid of that 2, I'm going to have to put in a half there. So 2a times a half a t squared, the 2's will cancel, giving you a squared t squared. Okay. Now, does this look familiar? Well, looking up here at the first two equations we derived, ut plus a half a t squared, ut plus a half a t squared. So instead of all of this, I can write in s. Okay, so v squared equals u squared plus 2a. And instead of all of this, I'm going to write in s, because look, all of this is the same as all of this. So I'm going to write in s. And what have I got? V squared equals u squared plus 2as. And there's my third equation of motion. Okay, resistors in series. There's our battery. We draw two resistors in series with each other, one after the other. Okay, we call this one R1, this for R2. Now, with a circuit like this, we know whatever voltage we have here at our battery, let's just call it the total voltage. Okay, it's divided up among these fellas. He's going to get some of it, we'll call it V1, and this fella here, he's going to get the rest of it. Okay, and we know that his potential difference plus his potential difference is equal to the total potential difference of the battery. Okay, so VT, because that's the way these circuits work, equals V1 plus V2. Okay, now in terms of current, we know because it's in series, whatever current flows in here will flow out and will flow through this fella and flow around. So the current is the same all around the circuit. Okay, now from Ohm's law, V equals IR. Okay, so therefore the V total, okay, is equal to IR. Okay, so instead of V total I can write I. Now I is the same all around the circuit times R. Now the resistors aren't the same, so V total will be the same as I times R total. V1 then, okay, just looking at this fella here, okay, is V is equal to IR, so V1 is going to be the I. Now I is the same for him and him and him, okay, so it's got I times R1 plus, instead of V2, we can write V equals IR. So instead of V2 we're going to write IR. I is the same for this fella as it is for him, times R, and in this case it's R2. Okay, is anything common there? Well, the i's are common, so if I divide right across by I get R total is equal to R1 plus R2. So the total resistance, you simply add the first resistance plus the second resistance, and that gives you your total resistance. Okay. Resistors in parallel then. Battery. Now there's our two resistors in parallel. Okay. Now for a parallel circuit like this, we know whatever voltage, whatever potential difference we have across that battery, each of these resistors feels the exact same potential difference. Okay, because these fellas here, they're all connected here to the same side of this battery here, and on this side here, each of these fellas here is connected to this side of the battery. Okay, so whatever potential difference exists between here and here, well look, it's the exact same between here and here, and it's the exact same between here and here. Okay, so if a potential difference across the battery is V, this resistor here, which I'll call R1, has the same potential difference, and this resistor here, which we'll call R2, has the same potential difference, V, V, and V in each case. Okay. What about the current? Well, current will flow through the battery. It comes here to this junction. Okay, the current into the junction will then split. Some of it will go this way and some of it will go this way. So let's just call it I total. When it comes to this junction, it splits. Some of it comes out here, we'll call it I1, and then some of it, called I2, will go through this fella here. Okay. When the two currents go through the two resistors, then they'll come out the far side, they'll come to this junction, and they'll join up again, and they'll continue here as I total. So there's I1 going through R1, then I2 will go through R2. They'll join at this junction here again, becoming I total. Okay, like that. Okay, so let's look at the total currents. So total current is equal to the I1 plus I2. I1 plus I2. Okay, now from Ohm's law, we know V equals IR. V equals IR. Now in terms of I then, so therefore I is equal to, well, bring your R across, it'll go under the line, V over R. Okay, so I'm going to rewrite this equation here using V over R. So instead of I total, I'm going to have V over R. So V total, and it's just a V. Okay, V is the same everywhere. So it's just V over R total equals, instead of I1, the current going through here, it's going to be V over R. The potential difference across R1 is just V over R1. Instead of I2, it's going to be V over R. Here's I2. It's V over R2. Okay, now is there anything common here? Well, yeah, V's are common, so I can divide across by V's to get rid of those. So divide across by V gives you, dividing each of these by V, cancel out the V on top, I'll be left with a 1 over RT equals 1 over R1 plus 1 over R2. And there's the equation there for resistors in parallel. Okay, so we know the force on a current carrying conductor in a magnetic field is given by this, F equals B I L. Okay, so we know that. Okay, now let's consider a charge Q moving through a conductor of length L in a time t. So here we are. Here's our conductor. The wire basically has a length of L. We have a charge Q moving through it, okay, in a time t. So consider a charge Q moving through a conductor of length L in a time t. Okay, now what formula do we have for charge? Well, we have current equals charge divided by time. Okay, we know that current is charge divided by time. And now what we're trying to get here, we're trying to get F equals B Q V. Okay, so if current is Q, so there's your Q, that'll be that Q there. Okay, now the V, what's our velocity? Well, we have velocity is displacement divided by time, or distance divided by time. So velocity is equal to displacement. Now this displacement in this case would be the L divided by time. So current is charge divided by time, velocity is displacement divided by time. In this case our displacement is the L, the length of the conductor. Okay. Now I'm just going to rewrite this in terms of just bring the T across, so that gives me L then is equal to V times T. Okay, so I have two little equations here. Whoa, little equations here. Okay, and I'm going to take each of these equations and I'm going to stick them into the equation that I know, F equals BIL. So F equals BIL, and subbing subbing. Okay, I get f is equal to b, stays as b, and instead of I, I'm going to stick in this equation here, which is q over t, and instead of L, I'm going to stick in this equation here. Instead of L, I have Vt, V times T. Okay. Now what happens here? Well, I've got a T under the line there, and Vt is the same as Vt over 1, effectively. So I have a T under the line, and that'll cancel with T above the line. So that'll give me F is equal to B times Q times V. That's it. Okay, diffraction grating formula next, n lambda equals d sine theta. Okay, this diagram is a bit tricky. Okay, so we're going to draw diffraction grating. Now diffraction grating is just a piece of glass or plastic with thousands of parallel lines etched on it, and between each line is a little gap. Okay, now we know when a wave passes through a gap, it diffracts, it bends. Okay, now the waves we're talking about here are light waves. So if a light wave comes along towards this diffraction grating, as it passes through this gap, it's going to bend. Okay, it's going to curve around, and we call that diffraction. So we're just going to draw the light wave after bending, coming through the gap like this, or the gaps, rather like this. Okay, there's our three wave fronts. Okay, after bending. Okay, now as each wave front passes through your diffraction grating, you simply draw a line at right angles to the wave front, and we're going to draw it dotted. So right angles to the wave front like that. So in other words, there's a right angle there. Okay, there's a right angle, there's a right angle. Okay. Now remember, these gaps are really close to each other. Okay, and these waves are, I mean, they're right on top of each other. Practically, they're really close. Okay. Now, if the waves are, two waves are on top of each other, they can interfere either constructively or destructively. But if they're going to interfere constructively, you've got to have a peak and a peak, or a trough and a trough. Okay, so in other words, if you've got a peak here, well, the wave that's right beside it has also got to be a peak. Okay, now suppose when a wave came along to a diffraction grating, you had a peak. Okay, peak, peak, peak. So when this gets down here, this is also got to be a peak. Okay, and this is going to be a peak here, and this is also got to be a peak. Okay, for constructive interference to occur. Okay, or it could be a trough and a trough. Trough and a trough, or a peak and a peak. Okay, or else it'll be destructive interference. Okay, so for constructive interference to occur, okay, the extra distance that this wave is going to travel, okay, has got to be, if that's a peak and that's a peak, then from here to here it's got to be one full wavelength, or maybe two full wavelengths, or three full wavelengths. Okay, so it's got to be a whole number of wavelengths. Okay, now another word for a whole number is an integer. Okay, the extra distance, that the top ray travels must be an integer. Must be an integer number of wavelengths. In other words, it can't be half a wavelength, it has to be a whole number of wavelength. Okay. For constructive interference to occur, the extra distance that the top ray travels must be an integer number of wavelengths. Okay, so that's your first sentence here. Okay, so this distance here must be an integer number of wavelengths. We'll just call it n times lambda. Okay, n times lambda. There. Okay. Now, let's have another look at this. Okay, this are diffraction grating. These are our gaps. Okay, so the distance between these gaps here, I'm going to call it d. Distance between the lines, okay, is called d, and this distance here we've already established has to be an integer number of wavelengths. Okay, now just give me an angle here. There's my angle there, theta. Okay, and look what I have here, a right angle triangle. So that there is my right angle. like that. Okay, now what's the relationship? So I have theta, I have this line here is going to be the opposite, and this distance here is going to be obviously with the right angle, it's going to be the hypotenuse. Okay, so I have the t angle, I have the opposite, and I have the hypotenuse, so it's going to be sine. So sine theta is the opposite over the hypotenuse, is n times lambda over, in this case the hypotenuse of this right angle triangle is d. Okay, so just do a little bit of algebra here, so bring the d across, so n times lambda equals d times sine theta, and that's it. Okay, n times lambda equals d sine theta. Okay, so for constructive interference to occur, the extra distance that the top right travels must be an integer number of wavelengths, and from trigonometry here just write in n lambda theta d. I can see sine theta equals n lambda over d, therefore n times lambda equals d sine theta. Okay, so Newton's second law, what does Newton's second law say? Well, Newton's second law says that the force is proportional to the rate of change of momentum. Force is proportional to the rate of change of momentum. Okay, now how can I write that in terms of letters? Well, instead of force, I've got F is proportional to the rate of change of momentum. Well, change of momentum would mean the momentum before, after, or minus the momentum before. Okay, momentum. What's momentum? Momentum is mass by velocity. So it's going to be momentum after final momentum minus the initial momentum. Well, so mv minus initial momentum would be m times the initial velocity, which is u. Okay, so that's a change in momentum. Momentum after minus momentum before. The rate, well, the rate is to do with time, how quickly. Okay, so it's divided by time. That's the rate. Okay, so force is proportional to the rate of change in momentum. Okay, now I've got an m here common, so therefore force is proportional to, take out the m, it's v minus u over t. Okay, now does that look familiar? Let me see. Well, change in velocity divided by time. Okay, that was our junior cert expression for acceleration, wasn't it? Acceleration is change in velocity divided by time. So I can say F is proportional to m times acceleration. Okay, now if something is proportional to something else, it means there's a number, a constant, and when you stick it in there, it makes it equal to it. Okay, F is proportional to ma, that means F is equal to some constant times ma. Okay, now this is force is the unit of force is the Newton. What was the definition of the Newton? Definition of Newton was the force 1 Newton gives a mass of 1 kilogram and acceleration of 1 meter per second squared. Okay, so if you have 1 Newton gives a mass of 1 kilogram and acceleration of 1 meter per second squared, so you have 1 equals k times 1 times 1, so k has to be 1. Okay, k is equal to 1. Now you don't have to actually prove that, okay, but if k is equal to 1, therefore F is equal to 1 times ma, which is just equal to ma. Okay, that's how we do it. Okay, again, you just have to say k is equal to 1, okay, and F equals ma. Formula tables, page 51, definition of the radian. The radian is the arc divided by the radius. Theta equals s over r. Okay. So the radian, theta is equal to the arc s divided by, the length of the arc rather, divided by the radius. Okay, divide both sides by t, so you have theta divided by t is equal to s over r times t. Okay, now the angle divided by t, okay, is our angular velocity. Okay, how quickly the angle changes, so angular velocity, and look at this, S over T, displacement over time, distance over time is velocity, isn't it? Yeah. So velocity over R is still under the line there. Okay. Now we're looking for V, so just cross multiplying, that's like W over 1. Cross multiply, we'll give you V is equal to omega times R. Okay, and there's our equation for converting between linear velocity and angular velocity. Okay, now for this one we're talking about a satellite. Okay, so suppose that's the Earth. And here's our satellite travelling around the Earth. Okay, it's travelling around a circle. And the centre of that circle is the centre of the Earth. And the distance from the centre of the Earth to the satellite will be the radius of our circle. Okay. Now the centripetal force, or the force that stops the satellite from spinning off into space, is called a centripetal force, and the formula for centripetal force is given on page 51 of our formula tables. That's it there, mv squared over r. Okay, so the centripetal force, the force that stops that satellite from flying off, is equal to mv squared over r. Now it's also, of course, the force of gravity, because that's what's attracting the satellite to the Earth in the first place. And the formula for the force of gravity is on page 56 of our log tables. It's Newton's law of gravitation. Okay, big G mm over d squared. Okay, so the centripetal force can also be given as G times the mass of the satellite times the mass, big M, of the Earth over the distance between them squared. Now we're using the r because the distance between them is the radius of the circle. Okay, so I'll just call it r squared. Okay, now so this equation here is the same as this equation. There are two equations for the force that holds the satellite orbiting the Earth. So I can divide by r, and I can also, I can divide by m, there's a little m in both of them, and I can also multiply both sides by r. Okay, to tidy it up a bit. So dividing both sides by m, those m's will cancel. This is the m of the satellite now, mass of the satellite, and multiplying both sides by r, one of those r's there will cancel. So I'll be left with v squared equals g m over r. Okay, and this in itself is a very useful equation. Okay, now the period now, so we're trying to derive an expression for the periodic time of the satellite. Okay, now the period is the time it takes to go in one complete oscillation. Okay, here's our satellite going in one complete oscillation around the Earth. Okay, now how long does it take to go around in one complete oscillation? Well, we know speed or velocity. Speed is equal to distance over time. Okay, now the periodic, we're looking for the time. Okay, so the periodic time then is equal to the distance divided by speed, or distance divided by velocity. Okay, and distance divided by velocity, because it's a constant speed. Okay, distance divided by velocity, and the distance travelled. Well, how far does a satellite travel when it's going around in a circle? Well, it's the circumference of a circle, isn't it? Which is 2 pi r divided by the velocity of the satellite. Okay, so the periodic time t is equal to 2 pi r over v. Okay, time it takes the satellite to go around is the distance travelled, 2 pi r divided by v, the speed it's moving at. Okay, now squaring both sides, t squared is equal to, square this, you get 4 pi squared r squared over v squared. Okay, and then look up here. Here I have an expression here for v squared, so if I stick this expression in instead of this expression here, like that, okay, what do I get? I get t squared equals 4 pi squared r squared divided by, now I'm dividing by a fraction, and dividing by a fraction is the same as multiplying by the inverse of this fraction. So flip this fraction upside down and multiply by it. So that'll become r over gm, and multiply in by that. So the gm will be multiplying into the bottom, and r will multiply in on the top. Okay, now I already have an r squared there, so that becomes t squared equals 4 pi squared r squared times r will give you r cubed over g m. Okay, check our log tables just to see if we've got the right expression. And on page 56 of our log tables, t squared, there we go, equals 4 pi squared r cubed over gm. And that's it there. Okay. Okay, so we're shown if something obeys Hooke's law, it also executes simple harmonic motion. Okay, now if something obeys Hooke's law, well, Hooke's law is on page 57 under forces. Okay, here it is up here. Okay, if you stretch a spring, the restoring force is equal to a constant times the displacement. Okay, or the distance you've stretched it. Okay, so if something obeys Hooke's law, says that force is equal to minus k, a constant, times the displacement. Okay. Now, this is the force. Okay, so the restoring force. But force, we also know, is equal to force is also equal to mass times acceleration. Okay, we know that. Okay, so therefore these two must be the same as each other. So mass times acceleration must be equal to minus k times s. Okay. Now move the m across. Acceleration then is equal to minus k times s all divided by m. Okay, now we're trying to show something obeys Hooke's law. Hooke's law that also exhibits or executes simple harmonic motion. Well, what's simple harmonic motion? We have an expression for anything exhibiting simple harmonic motion, and here it is here. Okay. The acceleration is equal to minus omega squared s. Okay, and look what we have here. If I group this together like this, okay, a is equal to minus this expression times s. Okay, so I effectively have the same equation. Okay, so this is equivalent to an equation for simple harmonic motion, which says that a is equal to minus omega squared s. Okay, where omega squared in this case would have to be equal to this, minus k over m. And that's it. Okay.